Hello, I am Dr. David Kordowitz, and welcome to Computer Programming. Today we are going to talk about the historical context of computer programming, as well as provide a brief introduction to how compilers work and what different steps are involved in compiling code. Let's start from the beginning. The first computer programmer was Ada Lovelace, who was the daughter of Lord Byron. Because of Lord Byron's political clout as well as financial connections, he allowed Ada to meet many people of great importance in Great Britain at the time, and managed to get her to meet Charles Babbage, who was a mathematician who was doing some very interesting work at the time. He had developed something known as the difference engine, which was widely regaled as the first modern computer. It was basically a giant mechanical device that would allow you to compute polynomial numbers. He built a working model of this device in 1822, which he then charged Ada Lovelace with programming, and we'll show you what she did. The first program basically computed some exponents and allowed calculating Bernoulli numbers using just the computational abilities. This was a very difficult problem at the time and really had no proper solution. The British government thought that computers would be really important and wanted to spread them for military and civilian use, and provided £1,700 to continue through this process. However, it was much more expensive to create these due to the metalworking of the time, primarily not using the type of equipment you would see today. Therefore, it became very impractical and cost prohibitive to build computers to distribute out into the real world. That said, this first model definitely worked and showed the potential of using computational power. Now that said, the technology had to advance enough to reach to the current day, to reach to what we have in our current day computing setups. This took a while, but in the 1960s, almost 100 years after Charles Babbage's difference engine, the modern computers started to appear. Now, the old computers were largely built of vacuum tubes and things like that. They were large, they were noisy, they had moving parts, all things that today, on the whole, we wouldn't even consider. So it's basically, the modern computer was based on transistors or vacuum tubes. They can be used somewhat interchangeably. However, the computers of today are using basically microscopic transistors. And basically, the reason we like using transistors for logic is that it has two states, 1 and 0, true and false, on and off. So when programs are created, they simply can output whether something is on or off. And as you build up further, all you're doing is solving simple logic problems using a true and false type setup. Machine language is something that very early on was developed and also theoretically exists for anything you build. Machine language basically is ones and zeros, trues and false, that go into your logic design, that go into your logic system and allow the program to do what it needs to do. Now, most computers today use arithmetic logic units that can do some advanced things, but at its basis, the two operations that computers need to be able to do is add and multiply, and we'll sort of see how that works as things go further. A little bit of history here is that machine code really doesn't help you very much. It's not readable, it's all ones and zeros, and unless you know exactly what the hardware is doing, ones and zeros make no sense. So some of the chip manufacturers developed what we call assembly language. And what assembly language is it basically is a processor-specific language that allows you to put commands that look somewhat human readable together to create code. On the right, you can see a program that is built in assembly language, and you can see basically that it sort of looks like text, but it has a certain format to it. Now, when assembly language was first developed, each instruction here and each part of the instruction is translated directly to a binary number or a binary word, which is in machine code. So basically, the code you write in assembly can immediately be replaced one-to-one with machine codes that will operate on the processor. This limits your abilities in assembly language, and it also means that it's still fairly low level, and when you write a program in assembly language, basically the assembler converts it over to ones and zeros, and then it runs at pretty much as fast a speed as machine language. This, however, really isn't the best way for a programmer to become involved in developing things. Assembly language is useful for certain platforms and certain problems, but it's not really practical for writing most things. In the 1950s, people started to develop what we call higher level languages or higher order languages. And these languages started using text or commands that were much more human readable. Some of these languages are things like Fortran, C, C++, Java, COBOL, Snowball, BASIC. If you want to look up a list of these languages, there are thousands of them. Early on, these languages were done on punch cards using hollerith code, like you can see on the right, and modern day programmers just simply use text editors and write the commands out and use a program to compile or interpret their code. High-level languages are really easy to program, but we've lost the one-to-one correspondence. So what that means is somewhere along the way, you have to have something that's translating to processor commands. This then leads to these programs running a little slower. What that means is if you want very, very high speed, you want to get as close to machine language as possible. But if you want simplicity in coding, higher level languages make your life much better. There also is sort of a hierarchy in higher level languages as to program speed and program execution speed. So typically Fortran is one of the faster languages, where things like Java tend to be a little slower. C and C++ are very fast languages, though still can't reach the efficiency of Fortran. That said, you should program in the language you're most comfortable with, or in the language that most appropriately solves the problem you're trying to solve. This means that not every program should be in the same language. That said, the theory for any one of these languages is interchangeable with some syntactic differences. So for the purposes here, we're going to be talking about C, C++, and MATLAB. Higher order languages go through either what we call interpretation or compilation. In compiled programs, we first go through and we convert the program into something runnable. This is done at the time you write the program. So in C or C++ or Fortran, you write a program, you compile it, and then the output of the compiler is your executable that you can run. In interpreted languages, such as Python and things like that, the computer actually translates the instructions at runtime. MATLAB does this too. As they are interpreted, they are executed. Interpreted languages tend to be really nice if you want to be able to debug and make changes while you're going, but they tend to be very slow because the computer actually has to do that translation from the high-level language to machine code at runtime. Therefore, if you're doing mission-critical, time-sensitive things, interpreted languages may not be your best choice. A little bit about C. C was developed first by ANSI, the American National Standards Institute. They founded a committee called X3J11 in 1983 to develop a new high-order language. This new high-order language ended up becoming C and was established in 1989 as C89. Please note, with C, they are standards, and it will be the same no matter where you're coding or who you're coding with. There was a time a number of years back that I had visited Israel, and there was somebody working on some code there who needed help with some of their C coding, and I sat down and realized everything was exactly the same. It was in English, and then you start thinking about, yes, this is a standard, and This is not only an American standard, but in 1990 became an international standard. Now, C89 was the American standard, but when ISO approved it in 1990, it became C90. What this means is C90 and C89 are the same thing. They're exactly the same. That said, currently we don't really use C90 or C89 anymore, but all the basics we're going to cover in this class fall under C90, C89 type standards. There have been revisions in 1995, 1999, 2011, and 2018. There are expected revisions coming up, but you have to remember that every time that these revisions come, features are added to the standard. They're not taken away. What that means is the code that was written in C89 in 1989 can still be compiled just as well on a C18 compiler. So make that realization that C will continue to develop, but at the same time, there may not be, your code will still stay compliant as you go through it. So what is C++? So C++ is a superset of C. We will be using a little bit of C++, though the theory we're going to be talking about is mostly going to be C. In C, plus means increment, so it means increase by 1. So C++ is equal to C plus 1, so it's the next C. C++ primarily adds object-oriented programming as well as a few other things like streams and namespaces and things like that. We'll talk a little bit about object-oriented programming later in the class. However, for most of the things we're going to be doing, we're going to be working with the basics. And while it may seem easier to work in C++, and often it is, this complexity and increased availability of different things can sometimes make it less suited towards your programs. That said, you can compile C code in a C++ compiler, but the other way doesn't work. A little bit about MATLAB. MATLAB stands for Matrix Lab. It was basically developed University of New Mexico by Cleve Moeller. He was a computer science chairman, and basically the thing was that they were using Fortran and working with linear algebra packages, LinPack, LayPack, EastPack, IcePack. These are all different languages to do basic linear algebra operations such as multiplying matrices and finding singular value decomposition and eigenvalues and things like that. The problem is that working in Fortran with LinPack and LayPack and all those sort of things requires quite a bit of advanced programming skill. And especially when someone's looking at the math and looking how the math works, they don't really want to have to write all the extra side stuff to get it to be able to process and perform the linear algebra operations. So he partnered with a few people over in Stanford and another university, and they developed a program called MATLAB, which basically allowed the students to just work on the linear algebra algorithms and work on the mathematics side of things, but not have to worry about all the overhead of building your matrices and making sure that you can compile in LinPack and EastPack and all that sort of stuff. And they developed this and distributed it to their students. This started in 1977. It was available just to his students until about 1984, at which point they got together, and with the MathWorks being founded with Jack Little and Steve Bangert and Cleve Moeller, they were able to release what was known as MATLAB 1. Since then, MATLAB went for a while through the version numbers, so on like 1, 2, 3, 4, all that sort of stuff. And in about 2010 or so, they switched over to using the year, followed by an A or a B. A releases are released in the late spring or winter, basically late fall, early winter. And the B editions are released late summer, early spring, or early fall. So there's two versions. There's an A version and a B version available. Usually the B versions tend to be the ones with the major upgrades, though this isn't always true. If you have availability of a site license or something like that, you can always download the new editions and continue to upgrade as long as you're with your institution, and this would be recommended. Since MATLAB 2019, there is now an automatic updater built in that will give you an alert in the upper right-hand corner of your screen. This will only patch MATLAB as opposed to giving you the latest version. It will only give you the newest patch of the version you have installed. Also, be aware that when you install MATLAB on a computer, if you have a previous version, it will not remove it. It will simply run the two side by side. So what exactly does a compiler do? So compilers take high-level code such as C and convert it down to assembly or machine code. MATLAB uses what's called just-in-time compiling, so it interprets it the first time it runs it, and then if you haven't changed anything, it sort of has a compilation that it does that runs your code faster. Compilers basically start out by doing what we call scanning or pre-processing. What that is it goes through your code and pulls all the words out of it and figures out what all of these symbols are. That's things like variables and names of things and all of that sort of stuff. It figures out what all these are and puts them into what we call a symbol table. Symbol table basically is a way of storing the name of something and its value. It then goes through and does what we call parsing. In parsing, it goes through your code and it looks at both syntactic, so grammar-based things, as well as semantic analysis. So syntax is everything put together, and then semantic is what is it trying to do, and it develops a path of execution. So at the end of the parsing, you should sort of end up with something that tells the computer how to execute your code. The computer will then generate what's called intermediate code. This intermediate code is typically in a different language than your final code, and this intermediate code is the rawest version of your code that can be executed. This differs from compiler to compiler what this kind of looks like. From there, the code is then optimized to run faster and more efficient, which basically you can set the optimization level on most compilers. On the Arduino and MATLAB compilers, you cannot set those because they're sort of set the way they need to be set. Once your program is optimized, it goes through a step called linking. Linking goes ahead through your code and it converts that optimized code into something that the processor knows how to execute. This may differ by operating system, language, processor, all of these things, the actual target code that comes out. But it's important to know that the linker is what's actually translating your final optimized code into an executable program. Now, it's important to note in many compilers, you can do something called cross-compiling, which will actually use a different linker than the one for your computer. When you do this, it will generate binaries that won't run on your current operating system, but will run on the one of the linker you have chosen. So that's important to know. But this is kind of a high-level overview of how a compiler works. From here, we're going to look at different data types and how data works in your programs. I'd like to thank you for your time today, and see you next time.